Hello everyone, and welcome to this How We Built It talk, where I will be going over how we built the real-time viewer. My name is John Gibson, and I'm a software engineer for the real-time and big data team working on ArcGIS Velocity. So what is the real-time viewer? Well, working on ArcGIS Velocity, we see that users tend to have a harder time creating meaningful visualizations for real-time datasets, particularly with moving assets such as vehicles. With non-real-time data, often there is only one symbol on the map to represent some physical entity, whereas with moving assets, often you want to have multiple symbols tracing an asset's positions over time, and you may need to differentiate assets within the same layer using different symbols. So we worked on using the capabilities of the ArcGIS API for JavaScript to provide a map viewing application tailored towards these visualization techniques. In this talk, we'll be going over how we bootstrapped a new app using the ArcGIS CLI, scaffolding a new application with the components from the Esri design system, integrating ArcGIS API for JavaScript widgets into a React app, how we built a custom history lines visualization, some useful patterns for designing components that handle a variety of symbol types, and lastly, building React wrappers for integrating web components. But before we get into taking a look at the application and code, I'd like to first talk about our chosen tech stack. Me and my colleagues working on ArcGIS Velocity are all fans of React as our preferred framework for composing UIs, so we chose to continue to use it for this application. We also chose to use TypeScript for this project to be able to leverage the excellent type system that's provided by the ArcGIS API for JavaScript, and also to provide much needed structure for some of the pieces of our application that need to handle a variety of symbol types, which we'll talk about more in depth. As I mentioned, we use the ArcGIS CLI with its React output mode to bootstrap our application, and the output provided by that provided TypeScript out of the box. Note, however, we used the ArcGIS CLI back at the 4.15 release, which provided framework-specific outputs such as React, which used to be necessary to handle AMD module bundling. This is now no longer required in the current release of the ArcGIS CLI following the release of the ESM-based ArcGIS API for JavaScript, since it now can be used in a wider variety of environments and frameworks. For handling authentication and interacting with portal REST APIs, we also use the ArcGIS REST Auth and ArcGIS REST Portal packages. If you'd like a deeper dive on setting up authentication in your own custom app, then this year there is a talk on just that from my colleague Benjamin Schrader. And lastly, a lot of the visual components that you'll see that we used for the layout of the app, the controls for adjusting symbol properties, and iconography almost all came from Esri's design system. If you're interested in these components, this year you'll see that there are several technical sessions on the Esri design system, so definitely have a look at those. And now that we've covered the tech stack, we can finally take a look at the actual application. So at first glance here, we can see that we have a common layout for a viewer application. On the left, we have a primary panel for managing the data that's present in the map view. And we have a panel to display whatever widget we have selected. And these widgets are essentially just out-of-the-box widgets from the JavaScript API. Then, of course, we have the map view pane in the middle. And on the right, we have a contextual panel to display any widgets that are related to the selected layer. And what does that look like in code? So we see here in our app.tsx file that we have one shell for the entire application, and then we have the app's header, primary panel, web map, and contextual panel split up into their own React components. You may also notice that we are conditionally rendering this contextual panel based on the truthiness of this selected layer variable. And this selected layer variable is coming from a React context called map context. We found it very useful to use a React context to be able to store many of the objects from the JavaScript API that we're frequently working with, such as the map and the map view. So if we take a look at this primary panel component, we can see that this is a shell panel, and it has an action bar and a list of actions, each of which have their own string ID, and they all call an on-click handler, which essentially just takes that string ID and then sets that in local state. Or if it's already selected, it'll unset it to be able to hide the panel. whenever this state variable changes, active action, then the contents of what to render for that selected widget is recomputed from this useMemo hook, which essentially just maps between those string IDs to React components. And if we take a look at this layers panel component, we'll start to see a lot of the magic around using a widget from the JavaScript API within a React app. So down here we see that we have a plain div that we're going to use to mount our widget into, and we're using the ref prop from React. And usually you would use this with the result of the useRef hook, which we're not doing here. This widget ref variable is actually a function which accepts the node once it's mounted and then does some stuff. This is called the callback ref pattern, and the importance of using it here is so that we get an access to the underlying DOM node, but what we really care about persisting and working with throughout the rest of the component is the instance of the layer list widget that we're going to create. So down here, once we know that the node is not null, it's been mounted, we take that node and we pass it as the container for our layer list widget. And we also pass a function which defines some actions that can be taken on a layer as it's created in the layer list widget, which would be like zooming to that layer or zooming the map to be to fit the extent to the best fit for the layer. And then we're also taking that new instance of the layer list widget and we're attaching a event listener so that anytime a selected item changes within the layer list, we take that selected layer and then set it within our map context to keep track on it throughout all of our other connected React components. And then lastly, we take that instance of the new layer list widget and we set it as a state variable. And because now that it's tracked in local React state, we can use that within our use effects and use memos throughout the rest of the component to trigger changes whenever that widget is first created. So now that we've taken a look at incorporating widgets from the JavaScript API, let's take a look at one of the custom real-time visualizations. For moving assets, oftentimes it's useful to be able to not only have one dynamic symbol on a map to represent an asset, but instead show several of the asset's most recent locations over time. With this history line style, we can specify how many observations to display, specify a symbol for the most recent observation, specify a separate symbol for any previous observations, and specify a line symbol for the polyline that will connect the observations that make up the track. We can also go in and change the latest observation to be some sort of directional symbol and rotate that symbol off of attribute data so that we can get a sense of where that asset is headed. So, how did we build this? Essentially what we did is we created this history lines layer class, which extends the graphics layer from the JavaScript API. And an important thing to note here is that we have a property called observations by track. And what this is a map that's persisted within this instance of the class, and it essentially maps track IDs to all of the graphics that are associated with that track. We can see that to construct this, we take in a time info object, and essentially that just contains the track ID field that we need for joining together data. We have settings, which is a custom interface, which essentially just contains all of those sort of symbols and setting values from those UI controls that we saw previously. We have graphics layer properties, which essentially is just any properties that need to be passed to the underlying layer, such as the ID to use and visibility. And visibility is an important thing to note here because since this layer is meant to be an alternative visualization for our stream layer, and since this layer is still being added to the map, we want to have it be essentially hidden within any widgets that might show these layers, such as the layer list. So that the user only has the sense that they're interacting with the stream layer. And if we take a look at the add observation method, essentially every time the stream layer receives some observation, it's going to have this stream layer view data received event object, which contains some attributes and geometry. And first, we destructure those styling settings that we saw earlier. We go and look at what the track ID is from this observation's attribute data. We go and find the matching track, which is the polyline, the instance of the polyline associated with that track. And if that exists, then we go ahead and we clone its geometry. We create a new set of coordinates and push that onto the polyline. We take into consideration that maximum number of observations that the user has set. So if the new path length is now longer than what is allowed, we go ahead and splice that array of paths to get rid of the oldest one, to make sure that it is still fitting within that max observation count. And then we go ahead and update the track's geometry with that newly constructed geometry. Otherwise, if that track was not found, we go ahead and construct a brand new polyline using the geometry as the first node. And also, the symbol here is we continuously contain a reference for what that trackline symbol is, and then anytime we need to construct a new graphics with it, we clone it. We also do this for the latest observation symbol and the past observation symbol. So down here, we also need to not only just create a new node or a new instance of the polyline, we also need to create the new point symbol to go on the track. So we cloned that latest observation symbol. We also grabbed the observations from that map that we saw earlier, passing in the track ID. And then we take into consideration whether or not the user has specified to rotate the latest observation by some sort of attribute data. Whenever that toggle button to say that I do want to rotate off of attribute data is selected, then these settings are populated with some default values. So whatever that rotation type is, whether it's geographic or arithmetic, we do the calculations there and set that as the symbol angle. We also need to go ahead and replace what is now the second most recent observation is. We need to replace that. Currently that instance of that symbol has the symbol for what would have been the latest observation, and now we need to go in and take the existing angle that was on that instance of the symbol. We need to preserve that, but essentially now clone the past observation symbol and assign that to it. Next, we construct a new instance of the graphic using that symbol and the geometry that we've built up, passing in all of the attributes so that can be shown in any pop-ups. And lastly, if this is the first time that we're receiving an observation and there were no previous observations for the track, then we go ahead and build a new array of observations and set that within the map. Otherwise, we take that existing array and then push in the new graphic. Once again, we consider whether this is now exceeding that max observations, and if so, we go ahead and splice that array. And lastly, add that new graphic to this graphics layer. And essentially what happens from there is that, without going too deep into other app internals, is that anytime the user activates this style, the history line style, then we register an event listener on the stream layer for any new data received events. We instantiate this new custom graphics layer and add it to the map. And then we also, for the duration of while this graphics layer is active, we hide the underlying stream layer so that it's no longer visible. And then do the reverse if this style is deactivated or we switch to a different renderer. Next, I'm going to talk a little bit about how we created this the symbol styler, which is this panel that we use for configuring all of the different point, picture, and line symbols throughout the application. At first, while working on the history line style, we only provided one fixed point and line symbol for the track, and we knew that for this new component, to be able to accommodate not just the history line style, but also single symbol and unique values rendering, that we needed to approach its design as generically as possible. We wanted to avoid rendering different components, for example, needing to render a component that's specific to point symbols for the latest and past observations, while having to render a separate component specific to line symbols here for the track line. We wanted to have a single component that could accept any symbol and internally handle which corresponding controls it should render. Luckily, the ArcGIS API for JavaScript helped make this manageable, since many of its classes have a type property. So if we look back at the code, so this is the symbol styler component we created, and as we can see, it has an open symbol styler method. This method is exposed by a React context that can be used wherever we have a button to open it. You'll see that it accepts an options argument, and if we take a look at what that contains, we see that it requires a clonable symbol, and what this clonable symbol type is a union between 4 of the types from the JavaScript API: simple marker symbol, simple fill symbol, simple line symbol, and picture marker symbol. And the important thing to note about these is that all of these have a type property. If we look here at simple marker symbol, for example, we can see that this is a read-only property, which is just simple dash marker. And the important thing is that because all of these have that type property, our union forms what's called a discriminating union in TypeScript. And the nice thing about that is that down here, we have a use memo hook that computes what content should be rendered in the popover, essentially all of the controls for the selected symbol type. And in here, because all of those, that type property, all of the values are present and unique, that acts as a type guard. So the TypeScript interpreter is able to know within the body of each of these case statements what the type of, for example, here our options.symbol property is. We see here that because this is both a simple marker case and picture marker case, that the symbol is either of those two. It formed a new union type out of the two of those. So it took some time to come up with this design, but once the groundwork was in place, it became surprisingly fast to add support for new symbols and allow for far more extensive customization for these symbol types throughout the app. It was as simple as using that open symbol styler method wherever we had a button to show this symbol customization panel and apply that new symbol during the onChange callback. For our last section, I'd like to talk about some of the patterns around integrating web components from the Esri design system into a React application. Since the Esri design system provides web components, we interact with them using standard DOM APIs. Here we have the size slider for simple and picture marker symbols, and what this calcite slider component is a React component that acts as a wrapper around the underlying calcite slider element from the Esri design system. It accepts many of the same attributes as props. However, here, since we're using JSX, we can accept a lot of these props as numbers, and whenever they're passed to the underlying element, the standard DOM APIs will do the work of stringifying those prop values for us. And while it's nicer to be able to use more explicit types, the main advantage of using this wrapper pattern is to be able to abstract away the concepts of registering event listeners. So here we are using a ref with the useRef hook from React, and we're passing that ref to the calcite slider element. And once that's defined, then we use the use effect to be able to attach an event listener onto that DOM node, listening to the calcite slider update event. Here for this application, since dragging the slider will be continuously updating symbols, and updating a lot of symbols within the map at once could be very overwhelming on the browser performance-wise, we decided that we wanted to be able to debounce the events here. So we did assign a default debounce wait time of 500 milliseconds and then use that with the debounce function coming from Lodash, so that as the user is dragging it, our app will wait until there hasn't been any interaction for at least 500 milliseconds before taking whatever the value currently is and then applying that to the symbol. So back within the symbol styler component, because of using this wrapper pattern, we use the calcite slider component 5 times, which means that we don't need to maintain 5 separate refs and attach event listeners 5 separate times within this same component, which helps to keep all of our React code cleaner. And that concludes our agenda for this talk, so thank you very much for listening to this walkthrough of our experiences, and please provide feedback for this session by using the survey link provided below.